In this recording, we discuss what happens when we have more than one slit. For example, here we have 1, 2, 3, 4 slits. Okay, now in this particular case, if we have, remember like in the other case, a light beam that's going to be divided into these different beams from each of the sources. If we come at this particular point, the light that's going to arrive to this point is going to arrive from the top slit through path 1, bottom slit, second slit, path 2, path 3, and path 4. The question here, let's compare the first two slits. And in this particular case, we would like to make sure that the slit separation is the same in all cases, so it's the same D. Now, if the path difference between beam 1 and 2 is such that, remember this is our path difference, is such that d sine theta is equal to lambda, the two waves are going to be in phase, interfering constructively at this point. Now, if that's the case, then what would be the path difference between beam 2 and beam 3? Since I have the same separation here, D, that's the path difference here. That's the same as this. So the path difference between beam 2 and beam 3 is also d sine theta. So that means beam 2 and 3 are also interfering constructively. Similarly here, I still have the same path difference here. Since I have the same D, remember the angle here, because L is so large, I have the same theta here, here, all of them are the same. So I again have the same path difference d sine theta. So the beams are going to be in phase again. So what does that mean? That means all of these beams are going to add up constructively there. In other words, what I just talked about, the path difference between the first two is d sine theta. But between the first and the third beam, it is actually twice d sine theta, or twice lambda. Between the first and the fourth is 3 times lambda. Still we have constructive interference. Which means here, my condition for constructive interference is the same as the condition for constructive interference when we had 2 slits. All what we needed to have is that d sine theta is equal to n times lambda. Okay, let's look at this example. We have 3 rays that are interfering constructively at the shown point. Now, if the intensity coming from ray 1 is I0, intensity from ray 2 is I0, and the intensity from ray 3 is I0 as well. The question is, what would be the intensity of the light beam when they all 3 meet at that point? I'm going over this, but it's a tricky question because of what we know about the intensity of light, which is not much. The intensity of light is actually proportional to the electrical field squared, or proportional to the magnetic field squared. Now, when the waves add up, when we think of the waves, remember we think of the electrical field or the magnetic field. That's what an electromagnetic wave is. So actually, what's going to happen here when the 3 waves are going to add up, it means I'm going to have 3 times E, or 3 times B. The 3 amplitudes are going to add up. Now, the intensity is going to be the square of that. So it's going to be 9b squared, which is 9I0. So this is my answer. So when I have 3 light beams adding up constructively in one point, the intensity is going to be 9 times the intensity of one of them. Now, let's look at this a little differently. What if beam 1 and beam 2 are interfering destructively in this case, meaning the path difference between them is lambda over 2. Okay, so they add up destructively. What's going to happen to the third ray? Are we going to have a minimum? When they add up destructively, a trough and a crest adding up destructively, so we have 0 there. This is going to be left alone and not cancelled. So meaning that I'm not going to have a minimum. I'm going to have some light. The light from the third that's going to remain there. In other words, if we look at it, this is where all 3 are going to add up. The intensity is 9I0. But then, when the path difference between 2 of them is lambda over 2, but then 1 is going to be left out, I'm going to have an intensity of I0, that's due to the third one, and the other 2 are going to cancel out. Somewhere in between, I'm going to have all 3 of them canceling out. Now the phase difference, instead of being half of lambda, it has to be 2/3 of lambda for them to add up destructively. When I have 2/3 of lambda path difference, I'm going to have destructive interference. You get the idea. Now, how does this look like? Remember, this is calculated by computer. So this is going to be what we call my principal maxima. And they are going to be at the same positions given by d sine theta is equal to n lambda. And halfway in between, I'm going to have secondary maxima you see they are less bright than these. Now if we are using white light, the middle is white, and then we have our secondary maxima here. Now what if I have more than 3 slits? Again, at the positions where I have d sine theta, the path difference being equal to lambda twice lambda, and so on, whenever we have that path difference, I'm going to have maxima, principal maxima. Now these maxima are going to get thinner and thinner. Notice here, remember initially the maximum extended all the way to here and here. Now it is thinner. Now when we go to, for example, 10 of them here, it's going to be even thinner. And I'm going to have secondary maxima there. The principal maxima is going to be due to all 10 rays adding up, meaning that the intensity here is going to be 10 squared I0 or 100 I0. And then for the secondary maxima, it's going to be a more complicated story. There's going to be, if I have 10 slits, some of the 10 are going to add up, but not all of them. And then you see actually the secondary maxima, we are going to get them with different intensities, depending which ones are going to add up constructively and which ones do not. And we are not going to get into that in this course. We just know it's going to be a little bit more tricky. The key point here, the positions the principal maxima is going to be the same as in the case of a two-slit pattern. They're going to be at exactly the same position. The only difference is they're going to get thin. Okay, here are other examples. This is 3 slits. In this case here, now for 3, how many secondary maxima we have? 1. Okay, now here, 1, 2, 3, 4, 5. This is when we have 7 slits. Okay, and then this one here is a little more, and you notice their brightnesses are not the same. I don't remember how many slits do we have here. Okay, let me not answer it. I don't remember how many. But the more slits we have, the thinner the principal maxima are, and we have less prominent secondary maxima. Okay, now the key here, we still have the same equation. D sine theta is equal to n lambda. The same equation as the equation for a double slit experiment. That's the equation that we use for identifying the position of the principal maxima. Okay, now I'm going to use WebTop again to demonstrate what happens with multiple slits. Okay, I have 2 slits here. What I'm going to do, I'm going to, let's see, what am I going to do? I'm going to put them, okay, that's all right, probably at this separation. And then I'm going to increase this to 3 slits. Okay, you notice here my intensities. Notice there it's a 9, this is a 1. And actually here, if you notice when I position my cursor here, it reads the intensity for me. And the intensity, you can read it at the bottom here. The values, you read it there. So for example, here I'm getting close to the 9, and then it drops, and essentially we are at 0 here. And we get close to 1 somewhere there, and go back to 0 and so on. Okay, now we are seeing this for blue light. Now the position for the maxima, notice here how many do we have? 1, 2, 3, and then portions of the others. Let's go back to 2. Same thing. So the position of the maxima does not change. That's important. Let's go to 4 slits. There's the 4 slits. Okay, now here the number of secondary maxima is going to be 4 minus 2. The other one, 3 minus 2, it gives us 1. Here, 4 minus 2, we have 2 of them. And look at the intensity here. It's again close to 1, and here we are at 16, 4 squared. Okay, what about if we have 5 slits? Okay, here we have 3 secondary maxima. The middle one is smaller than the other 2. This is, we are seeing about a little bit more than 1 for the intensity, while here, I'm not sure if the simulation is showing it correctly, but we are going to 1, and here it's 5 squared, so we should go to 25. Okay, what about 6? Okay, now 6 squared is 36. That's the intensity that we have. We still have them at the same position. You notice how thinner they are getting. Now I have 6 minus 2, 4 secondary maxima, 2 identical ones here and 2 smaller ones. Now you guess it, what if we have 7? If we have 7, So it should be 5, 49 for the principal maximum, same position but even thinner, 5 secondary maxima, the 2 larger ones here, and then 2 others that are identical and 1 in the middle. And you get the idea. Okay, if I go to 9, I'm skipping 1 now. Okay, there is a slight problem here with the simulation. And so it is very thin. We have the secondary maxima are very difficult to see now, but we have 2 here. Oh, you can count them here, possibly. Okay, we notice there is a problem with the simulation. It seems it's not operating very well here, so that's why we're not seeing everything correctly. But 1, 2, you get the idea. They should be, if we have 9, there should be 7 principal maxima there. Count them 1, 2, 3, 4, 5, 6, 7.